this lecture, we're going to be looking at polynomial functions of higher degree, and in particular, we're going to focus on the end behavior of polynomial functions. The end behavior is a way to describe how the function behaves as x decreases without bound, so as x goes to negative infinity, and as x increases without bound, as x goes to infinity. It turns out that if you know the leading coefficient of the polynomial and you know its degree, you can predict its end behavior. And here are the rules. Let f of x be a polynomial function with leading term a sub n x to the n. A sub n is called the leading coefficient because it's the coefficient on the highest power of x. N is called the degree that is the highest power of x. So here's the first rule. If a sub n is greater than 0 and n is even, then f of x goes to infinity as x goes to negative infinity, and f of x goes to infinity as x goes to infinity. Now what is that trying to tell us? It's telling us that on the left end, as x goes to negative infinity, the outputs of the function will be going to infinity, meaning that the left edge will be pointing up. That's the end behavior on the left side as x decreases without bound. And on the right side, as x goes to infinity, f of x also goes to infinity. So the right end is pointing up. That's the end behavior as x increases without bound. When the leading coefficient is positive and the degree is even, both ends point up. It might have any number of bounces in the middle, or maybe like a parabola, it will just bottom out and come right back up. But both ends point up. That's the end behavior of one of those polynomials. If a sub n is less than 0 and n is even, then we're going to flip that over. F of x will go to negative infinity as x goes to negative infinity, and f of x goes to negative infinity as x goes to infinity. Both ends point downward. And again, there might be any number of bumps in the center, but the end behavior is determined by those two characteristics, that the leading coefficient is negative and n is even. What about for odd degree polynomials? If a sub n is positive and n is odd, then f of x goes to negative infinity as x goes to negative infinity, so the left end points down, and f of x goes to infinity as x goes to infinity, the right end points up. We can't predict the behavior in the center based on those two characteristics, but the ends are set. The left end points down and the right end points up. If the leading coefficient is negative and n is odd, then we're just going to flip that over. F of x goes to infinity as x goes to negative infinity, the left end points up. And f of x goes to negative infinity as x goes to infinity, the right end points down. So we've got these four different end behaviors. Let me recap them. If the leading coefficient is positive and n is even, both ends point up. F of x goes to infinity as x goes to infinity or negative infinity. If a sub n is negative and n is even, then both ends point down. F of x goes to negative infinity, going in either direction as you go forever to the left or forever to the right. When n is odd, the behavior is opposite on each end. If n is odd and the leading coefficient is positive, then f of x goes to negative infinity on the left and it goes to positive infinity on the right. And if the leading coefficient is negative and n is odd, then we flip that over. The left end points up and the right end points down. Now these are rules that you can just memorize symbol for symbol, but what I like to do is use reference graphs, or what I call quintessential examples of each rule. If you can remember one function with those properties, and the fact that all functions with related properties point in the same direction on the ends, then you know the rule. Here's what I mean by that. I said on the first slide that if a sub n is positive and n is even, then both ends point up. I just need to be able to think of one example of a function with a positive leading coefficient and an even degree. And the example I think of is x squared. F of x equals x squared has a positive leading coefficient, the coefficient is 1, and the degree is even, the degree is 2. We know what the graph of that looks like. It's a parabola that opens upward. Notice that the left end points up and the right end points up, and that is the rule for that class of functions. All polynomial functions with a positive leading coefficient and an even degree will point up on both ends just like x squared. I use that as my reference example. That's how I remember it. That's my quintessential example. If a sub n is negative and n is even, we said that both ends should point down. My reference graph for that is the negation of x squared. I know that that's a parabola that opens downward. Both the end behavior on the left and the right is to tend towards negative infinity, just like a parabola that opens downward. If a sub n is positive and n is odd, I think of x cubed, which is that one that snakes vertically through the origin. We know the left end points down, so as x goes to a negative infinity, f of x goes to negative infinity. And we know that the right end points up. As x goes to infinity, f of x goes to infinity. By thinking of that one example, I know the rule for all functions that fit these two conditions. For a sub n less than 0 and n is odd, I think of the vertical reflection of that, negative x cubed. The left end points up, the right end points down. As x goes to negative infinity, f of x goes to infinity. As x goes to infinity, f of x goes to negative infinity. So if I'm trying to determine the end behavior of a more complicated polynomial, I use one of these as my reference and get my end behavior from that. Let me explain what I mean. This example says use arrow notation to describe the end behavior of the function f of x equals negative 2x to the fourth plus 5x cubed minus 7. I can't really tell you what this graph looks like exactly. I can pick off some easy things, like the y-intercept's going to be at 0, negative 7, and I can tell you the end behavior. The end behavior is based on the leading term, which, by the way, isn't necessarily the first term. We call it the leading term because it's the term that would be first if you organize the powers from largest to smallest. And that's what we have here. So this is our leading term. I notice that it has a negative leading coefficient. A sub n is negative. And I notice that the degree is even. The power is 4. We have a rule that tells us exactly what happens in that case. But rather than remembering this rule for symbol, I just think of my reference graph. Can I think of another function with a negative leading coefficient and an even degree? Sure, negative x squared. That's my reference graph. That points down on the left, so as x goes to negative infinity, f of x goes to negative infinity. That would also be true for the function we're investigating because all functions with this property behave this way. As x goes to infinity, well, f of x will go to negative infinity. All functions like this behave this way. Using this reference function, I'm able to fill in the blanks for this more complicated function. So I don't know what f of x equals negative 2x to the fourth plus 5x cubed minus 7 looks like exactly, but I can tell you that whatever it does, it points down on the left end and it points down on the right end. We'd have to do more investigating in order to figure out what goes on in the middle, but that we can tell just by looking at the leading term. Let me do another one. Use arrow notation to describe the end behavior of the function f of x equals 3/5 x to the fifth minus 4x squared plus x minus 11. An even more complicated function than the previous one. It has more terms, it even has a fractional coefficient. But when you're trying to determine end behavior, everything is based on the leading term, the term with the highest power of x, which again happens to be the first term in this example. I see that our leading term here has a positive coefficient. It doesn't matter that it's a fraction, it's a positive number. And I see that the degree is odd. N is odd. Can I think of another function with a positive leading coefficient and an odd degree? Sure, x cubed. X cubed is my reference graph. It points down as you go to the left and it points up as you go to the right. As x goes to negative infinity, x cubed goes to negative infinity. Well, that means that as x goes to negative infinity, our function will also go to negative infinity because it has the same type of leading term. All such functions behave the exact same way. As x goes to infinity, our reference graph goes to infinity, so our function must also go to infinity. You can go back and look at the rule. If a sub n is positive and n is odd, then f of x goes to negative infinity as x goes to negative infinity. That's how we filled in the first blank. And f of x goes to infinity as x goes to infinity, and that's how we filled in the second blank. We're following the rule, but rather than memorizing the rule word for word, I just remember the spirit of the rule, which is that all functions with the same properties of their leading term behave in the same way on the ends. So if I can think of an easy function and how it behaves, I can apply those same rules to the more complicated function. I'd like you to try this one. Use arrow notation to describe the end behavior of the function f of x equals negative 10x to the seventh plus x to the fifth plus x. You can either think of a function that has the same type of behavior, or you can just go back and look at the rules. Just reference the rules and use those. However you do it, try to fill in these blanks. I notice that the leading term has a negative leading coefficient, a sub n is less than 0, and the degree is odd, n is odd. My reference graph for that is the negation of x cubed. It points up as you go to the left. So as x goes to negative infinity, f of x goes to infinity. And it points down as you go to the right. As x goes to infinity, f of x goes to negative infinity. Last example, I'd like you to try this. Use arrow notation to describe the end behavior of the function f of x equals 15x to the 6th plus 9x cubed minus 7. I look at this and I see the leading term has a positive leading coefficient and an even degree. Both ends point up, just like in good old x squared, which is my reference graph. The quintessential example of a function like this is f of x equals x squared, and both ends point up. So as x goes to negative infinity, f of x goes to infinity, and as x goes to infinity, f of x goes to infinity. The end behavior is to point up on both sides. Now you can use end behavior for a bunch of different reasons, but the angle that we're going to take here is for sketching graphs and filling in sign charts. Armed with the knowledge of end behavior, we'll be able to get pretty good graphs of some fairly complicated functions without a whole lot of work. Let me show you what I mean. Here we're sketching the graph of f of x equals 4x minus x cubed, and I claim we can do a pretty good job of this by making a sign chart. We could do some upper level things to figure out what this looks like, but I claim that a sign chart will do the job, and our knowledge of end behavior will make this easier to do. First, let me get the sign chart created. F of x is this function 4x minus x cubed. We can't graph this using our knowledge of shifts and so on because of the x term. If it was 4 minus x cubed, we could just do a vertical reflection and shift the graph up 4 units, but the 4x kind of puts a damper on that. I'm going to factor this. This has a GCF of x. It's 4 minus x squared as my remaining factor. And then I can factor this to 2 plus x and 2 minus x. So my sign chart is going to have 3 numbers marked on it: 0, -2, and 2. And now here's where end behavior comes into play. If you're wondering what end behavior has to do with any of this, look at our function. The leading term is actually the minus x cubed. That's the highest power of x. It's not the first term, I know, but we still call it the leading term. It's got a negative coefficient and an odd degree. We've said that all such functions go to infinity as x goes to negative infinity, so I don't need a test point over here. I already know this is infinity because of the end behavior. All such functions start by pointing up. Similarly, the end behavior on the right, as x goes to infinity, f of x will go to negative infinity. I don't need a test point over there. So we've already got about half of this graph figured out. We know that there are x-intercepts at -2, at 0, and at 2, so I can plot those points. And I know that the graph is going to infinity as x goes to negative infinity, and it's going to negative infinity as x goes to infinity. All we have to do is figure out what goes on in the center. We could do that by plotting points, or if we just need a sketch, we can just figure out the sign. So like if I plug -1 into my factored form, the first factor is negative, but the next 2 factors are both positive. So this stretch is going to be negative, and that means that this part of the graph goes underneath the axis like this. But it's got to come back up and meet that point. It has to hit this point on the graph, so it must bend like this. Now how far does it bend down? Well, to figure that out, we'd have to plot a bunch of points. But the shape in general comes like this. At this point, we can fill this part in using some extra nerd stuff. Like if you look at the original function, it's an odd function. So it has symmetry through the origin. So the next part has to be up here. But we'll do it with the sign chart. If I plug in 1, it makes all 3 factors positive. That means that we're getting positive outputs on the interval from 0 to 2, and so it matches with what we said. That part of the graph must be above the axis. We get a pretty good graph just by making the sign chart. We're able to cheat on the sign chart by using end behavior on the left end and the right end. Let's try another one. Sketch a graph of f of x equals x to the 4th minus x cubed minus 6x squared, again by making a sign chart. We need to get that function factored if we want to make a sign chart. See if you can factor that. You would pull out the GCF, which is x squared. That would leave behind x squared minus x minus 6. And now we need to try to factor this trinomial. It factors to the product of two binomials. That's x minus 3 times x plus 2. And we have this in factored form. Make our sign chart here. The function's equal to 0 when x equals 0, when x equals 3, or when x equals negative 2. And to determine what's happening on the left edge and the right end, I don't have to plug in any numbers. I can use end behavior. This is a polynomial with a positive leading coefficient and an even degree. All such functions point up on both ends, just like y equals x squared. The left end must point up, the right end must point up. We can plot our x-intercepts that we found in the sign chart at negative 2, 0, and 3. And the left end points up, so does the right end. We just have to figure out what's going on in the middle. We can do that with some test points. I plug negative 1 in. The first factor is going to be positive because of the square. The second factor is negative. The third factor is positive. This is a negative stretch, so the function must bounce underneath the axis like this. Between 0 and 3, I plug in 1. 1 makes the first factor positive. Everything makes the first factor positive besides 0. 1 makes the second factor negative and the third factor positive. It did not switch, and so the function kind of bounces off of the axis and makes like a W shape. It's kind of a lopsided W because the x-intercepts aren't evenly spaced from the y-axis. We can get that graph just by making the sign chart. We only needed 2 test points because we filled in the edges of the sign chart using end behavior knowledge. We didn't actually have to plug anything in. Now at this point you might be wondering, do you really have to make a sign chart to draw this graph? No, you don't. Instead of coming up with the signs, you can just plot a point in those parts that you don't know. I'm pushing the sign chart because we can use the sign chart for other reasons. We use it in this class to solve inequalities. You might use it in calculus later to determine where a function is increasing and where it's decreasing, so you might use similar ideas. So I want to keep exposing you to the sign charts, but we don't really need a sign chart to draw this graph. We could have just come up with the end behavior. The left end points up, the right end points up. Plot those 3 x-intercepts. That was still a useful step, getting this factored. And then instead of making the sign chart, we could have actually plugged negative 1 into the function and got a point. Figured out where it was. Plug 1 into the function and get a point. Figure out where that is, and that would tell the story. Let's do one more example of this, and this is a slightly different form. Sketch a graph of f of x equals x plus 2 cubed times x minus 1 to the 4th by making a sign chart. This one is already factored for us. I'm going to rewrite the function down here, and we can make the sign chart. Negative 2 makes the first factor 0. Positive 1 makes the second factor 0. And now I'm going to use that same end behavior trick, but I have to think a little bit about what the leading term would be. If we were to multiply this out, its leading term would be x cubed. And if we were to multiply this out, its leading term would be x to the 4th. And if we multiplied those two things together, our leading term would be x to the 7th. The leading term here would be x to the 7th if we were to multiply this out. Well, that means that our polynomial has a leading term with a positive leading coefficient and an odd degree. And just like x cubed, that will start low and end high. It's got an x-intercept at negative 2 and an x-intercept at 1. The left end points down, the right end points up. And now we just need to know, what does this graph do? Does it come above the axis or does it go below the axis? You could actually plug in a number to figure that out. I'm just going to use the sign chart. I'm going to use 0 as my test point. 0 plus 2 cubed would be positive. The second factor is always going to be positive as long as x isn't 1 because of the 4th power, even power. So this part is positive, which means that the graph comes above the axis because the outputs are positive. And we got the sketch of that 7th degree polynomial with very little work. Using the end behavior here is a pretty nice trick, and we're going to pick up one more trick later so that we don't need any test points. Okay, so we've gone through the rules for end behavior of polynomials and done some examples of where we would use that knowledge to help us do other things. In this case, we were graphing. If you have any questions about the rules or how we created any of these graphs, Don't be afraid to reach out to me. You can send me an email or see me in an office hour.